Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Okay, so today we will continue with chapter 4, Digital Communication System Part 2. Okay, so basically we will directly continue to subchapter 4.3, which is pulse modulation. Okay, so this slide, this is actually the slide that is included in part 1, but this is actually covered in part 2. So if you want to find this slide, this is slide number 26 in chapter 4, part 1. Okay. So last week we have learned on the digital modulation technique. So basically there are three types of digital modulation technique. We have amplitude shift keying, frequency shift keying, and also phase shift keying. And today we will continue with pulse modulation. So take note, yeah, digital modulation and pulse modulation is two different things. So pulse modulation, there are several types of pulse modulation that we will learn today. So for pulse modulation, it is the mostly used modulation technique in digital transmission, and it consists of several processes. Okay, so the first process is to sample the signal, sample the analog signal, and then convert those sample signals into discrete pulses. And then lastly is to transport the pulses from the source to destination. Okay, so basically the input signal is analog signal, and then you convert it into pulses, then only you transport it. Okay, so there are several methods of pulse modulation. We have pulse width modulation, PWM. We have pulse position modulation, PPM, pulse amplitude modulation, PAM, and also pulse code modulation, which is PCM. Okay, so we will look into each method briefly, but the ones that we will focus on in chapter 4 part 2 is the pulse code modulation, which is PCM. Okay, so the first pulse modulation method is the pulse width modulation, and the short form is PWM. Okay, so why it is called pulse width modulation? It is because the width of a constant amplitude pulse is very proportional to the amplitude of the analog signal. Meaning when the amplitude of the analog signal varies, the parameter that is varied is the width. Okay, so the maximum analog signal amplitude produces the widest bandwidth, produces the widest pulse, and the minimum analog signal amplitude produces the narrowest pulse. Okay, so later on I will show you the figure to let you know the difference between the pulses or when the amplitude of the analog signal varies. And the second method is the pulse position modulation, or PPM. Okay, so the parameter that is changing here is the position of the pulses. So it's stated here, the position of a constant width pulse within a prescribed time slot is varied according to the amplitude of the sample of the analog signal. So meaning when the higher the amplitude of the sample, the further to the right the pulses is positioned. Okay. And the third one is the pulse amplitude modulation. So the parameter that is changing here is the amplitude. So the amplitude of a constant with constant position pulse is varied according to the amplitude of the sample of the analog signal. Okay, so when the amplitude of the analog signal varies, then the amplitude of the pulses also varies. So take note that PAM wave resemble the original signal more than the waveform for PWM and also PPM. And lastly is the pulse code modulation, or PCM. So PCM is where the analog signal is sampled and then is converted to a serial and bit binary code for transmission. Okay, so basically this is the ones that we'll focus on in this chapter 4 part 2. Okay, so this is the figure. Okay, so if you look at here, so the first figure here, figure A, is the analog signal. Meaning your input. This is your analog signal, the input. And figure B here is the sample pulses. Okay, the sample pulses. And C, D, E, and F is the pulse width modulation, pulse position modulation, pulse amplitude modulation, and this is pulse code modulation. So you can see the difference here. If you look at here, so the first one, the pulse width modulation, you can see that this is Vmax. So the higher the analog, the higher the amplitude of the analog signal, the wider the width of the pulses. Okay, the higher the amplitude of the analog signal, the wider the band, the wider the pulses, the wider the width of the pulses. So this one is the amplitude is small. Okay, it's a V minimum. So you can see that the width of the pulses is also smaller. Okay, so this is pulse width modulation. Okay, lebar. Width is kelebaran. And the next, this one, D, is the pulse position modulation. So if you look at here, when the higher the amplitude of the analog signal, the farther to the right the pulses. So the smaller the amplitude of the analog signal, the farther to the left is the pulses. Okay. So the parameter that is changing here is the position. The width and the amplitude of the pulses is constant. Okay. The width lebar and the amplitude of the pulses are constant. And the third one, this is pulse amplitude modulation. So meaning the parameter that is changing is the amplitude, the position, and also the width of the pulses is constant. So if you look at here, when the higher the amplitude of the analog signal, the higher the amplitude of the pulses. So the smaller the amplitude of the analog signal, the smaller the amplitude of the pulses. Okay, and the last one, this is the pulse code modulation, where it changes the analog signal into coded signal. Okay, so we will look in further into the pulse code modulation, where it changes the analog signal into several coded signal. Okay, so now let's continue to the second slide. So you can continue with the slide chapter 4 part 2. Okay, so this one. Okay, so now I will focus on pulse code modulation, or PCM. So PCM is the preferred method of communication within the public switch telephone network. Okay, why it is the preferred method? Because it's easy to combine digital voice and also digital data into single high-speed digital signal and propagate it over either metallic or optical fiber cable. Okay, so refer to figure of the simplified block diagram of PCM system. Okay, so this is the figure of the simplex pulse code modulation channel. Okay, so you need to understand this block diagram in order for you to understand the process of PCM. So basically, for a PCM, pulse code modulation, you can see that the input here is analog and the output is in analog. However, the process here, the process in between is in digital. Okay, so that is pulse code modulation. So the input analog signal, okay, the first step is it will go through a band pass filter. So the basic function of a band pass filter is of course to limit the frequency. So what it does is actually it limits the analog input signal to the standard voice band frequency range, which is between 300 Hz until 3000 Hz. Okay, and the output of the band pass filter is still in analog. After that, we have the sample and hold circuit. So the function of the sample and hold circuit is to periodically samples the analog input and convert the input into a multiple pulse amplitude modulation. So look at here, this is pulse amplitude modulation, where the amplitude of the pulses varies according to the amplitude of the analog signal. Okay. So the PM signal will then go to analog to digital converter or ADC. So what the ADC does is that it converts the pulse amplitude modulation to a parallel pulse code modulation, which are converted to serial binary data in parallel to serial converter. So basically what it does here, it converts PAM, pulse amplitude modulation, into pulse code modulation, PCM. Okay. So the output of the transmission line is a serial digital pulses, and then you have this regenerative repeater. So the function of this regenerative repeater is to regenerate the digital pulses. Okay, so over here, this is digital pulses. The function of this is to regenerate the pulses. Okay, same for this one. Until it reach this part. Okay, so this part is already the receiver. This part is the transmitter. Okay, so this is the transmitter. This is the receiver. Okay, so at the receiver, you have the serial to parallel converter, which converts the serial pulses received from the transmission line to parallel PCM code. Okay, and then you have the digital to analog converter, which convert the PCM here into multi-level PAM. Okay, it converts back PCM to PAM. And the whole circuit is basically a low-pass filter that converts the PM signals back to the original signal. So basically, this part here is this is PAM, and the function of whole circuit is basically to convert into the original signal, analog signal, and lastly you have the low pass filter. Okay, so this in the integrated circuit that performs the PCM is called codec or coder decoder. Codec. Okay, so for pulse code modulation, there are three main processes. So the first process is sampling. So the first process is the analog signal is sampled. The second one is quantizing, and the third is encoding. Okay, so this is your analog, this is your input signal, analog signal. So the first step is Okay, the analog signal is sampled. Okay, when you sample the output of the sampling, you got a pulse amplitude signal plus a pulse amplitude modulation signal. Okay, so you can see that the amplitude is changing with respect to the amplitude of the analog signal. Okay, and then the second part is the quantizing. Okay, the sample signal is quantized. So quantizing is actually giving values to the PAM. Okay, giving values to the PAM. Giving values. And lastly is encoding. So the quantized values are encoded as stream of bits. So the output of encoding, you have coded data or digital data. So these are the three main processes for PCM. So now let's look at the first process, which is sampling, PCM sampling. So the function of the sampling circuit is to convert samples to a series of constant amplitude pulses, okay, that can easily be converted to binary PCM code. So there are two techniques of sampling. So the first one is natural sampling. The second one is the flat top sampling. So natural sampling is where the tops of the sample pulses retain or maintain their natural shape. Okay. However, the natural sampling is difficult for an ADC to convert the sample to a PCM code due to unconstant voltage. Okay, so in the next slide, I will show you the difference between natural sampling and flat top sampling. And the second one is the flat top sampling. So this is the most common method. It is used in the sample and hold circle. Okay, so it converts the samples to a series of constant amplitude, pulse amplitude modulation voltage levels. Okay, so these are the difference between natural sampling and flat top sampling. So if you look at here, both of this is pulse amplitude modulation, PAM. The amplitude is changing. So this is the input waveform. This is a sample pulse. If you look at here, this is natural sampling. Okay, meaning the top of these pulses follows the shape of the input waveform. Okay, and this is the flat top sampling. So if you look at here, the flat top sampling, the top here is flat. Okay, instead of following the shape of the input waveform, now the top of the pulses is flat. Okay, but it follows the amplitude, meaning when the amplitude is high, then the amplitude of the pulses is also high. When the amplitude is low, then the pulses is also low. You can see that the top here is now flat. So that is the difference between natural sampling and flat top sampling. Okay, so when we deals with sampling, okay, we will deal with sampling rate. Okay. So stated here, this is the definition of sampling. It is a process of taking samples of information signal at a rate based on the Nyquist sampling theorem. Okay, so what the Nyquist sampling theorem say? Okay, stated here, the Nyquist sampling theorem stated that the original information can be reconstructed at the receiver with minimal distortion if the sampling rate in the pulse modulation signal is equal or greater than twice the maximum information signal frequency. So what it means here is that for PCM, with minimal distortion at the receiver, you must follow this rule where it stated that sampling frequency must be at least 2 times higher than the maximum modulating frequency. So what happens if the sampling frequency is smaller than 2 FM max? Distortion will happen or impairment will happen. And the distortion that we call as alias or fallover distortion. Okay, so you look at here, if the sampling frequency is less than 2 times FMX, alias or fallover distortion will occur. So this is the figure when Fs is bigger than 2 FMX. So this is Fs equals to 2 FMX. However, this is Fs smaller than 2 FM max. Okay, so you can see that there's a this is this shaded area. This is we have a fold over here. Dia bertindan. The signal bertindan. Okay, that's why we call it as fold over distortion. So because of this fold over, there will be information loss. There will be a distortion. Okay, and because of this, it cannot regenerate the original signal again if the sampling frequency is smaller than 2 FM max. Okay, so that's why you need to make sure that the minimum sampling frequency is 2 FM max. Okay, so the next the next PCM process is quantizing or quantization. So quantization is the process of assigning analog signal samples to a predetermined discrete level. Okay, meaning you determine the level or determine the value of the level. So the number of quantization level L depend on the number of bits per sample. So you can see that the number of level is equals to 2 to the power of n. Okay, so n is the number of bit and n is the number of bits. And the quantization levels are separated by a value of delta V. So delta V is V max minus V min over L minus 1. And delta V is also what we call as the resolution or the step size of the quantization level. Okay, for example, so this is a 3-bit PCM code. Wait, yeah. So this is the 3-bit PCM code. Three point five divided by okay. So if you look at here, this is a 3-bit PCM code. Okay, so you know that L the level is L 2 to the power of n, and n is 3. So your level here is 2 to the power of 3, and you will have 8. Okay, correct? 8. So that's why you have 8 levels. You have 8 levels. Okay, and then in order to determine the delta V, the resolution, so you know that the delta V is, V is V max minus V min L minus 1. So your Vmax is 3.5. Your Vmin is negative 3.5. Divide by L is 8 minus 1. So you will get 1. So that's why the resolution here is 1 volt. Okay, so from 2.5 to 3.5, 1.5 to 2.5, 0.5 to 1.5. Okay, so the resolution or the step size is 1 volt. Okay, so this is the figure to show this one. The first figure A is the analog input, and this is the sample pulses, and this is the pulse amplitude modulation. Okay, pulse amplitude modulation, and the D here is the PCM code. So basically, this is the process of PCM. From analog signal is converted to PAM first, then only is converted to PCM code. Okay, so if you look at here, so this is a flat top sampling. So this is the result of flat top sampling, pulse amplitude modulation, flat top. Okay, so from this, you can get the PCM code. So the amplitude here is 2 volt. So 2 volt is 110. And this one is negative 1. So negative 1 is 001. Okay, and positive 3 is 111. So basically the code, the PCM code can be written as, the PCM code for this figure can be written as 110001111. So this is the PCM code. Okay, so next is the quantization error. Okay, so it is the error that is produced during the quantization process due to the difference between original signal and quantized signal. Okay, so you can actually see the difference between original signal and quantized signal. Okay, so for example, is this figure. This figure actually shows you the original signal and the quantized signal. So the blue line here is the original signal, analog signal, and the red line is the quantized signal, meaning the pulse amplitude modulation. So you can see the difference. Okay, so the difference here is what we call as quantization error. And since a sample value is approximated by the midpoint of the sub-internal of the height delta V, then the maximum quantization error is plus minus delta V over 2. Okay, so what it means is that you can see that the value here of the quantizing, it takes the value, the middle value. Okay, the middle value. That's why it is stated that the maximum quantization error is plus minus delta V over 2. So the error lies between negative delta V over 2 plus delta V over 2. Okay, so this figure is actually just to show you. You can see that this part, you can see that the error is small. Okay, so that's why the error is small. And this part, you can see that the error is quite high. So that's why you have a high error. And next, the next parameter is the dynamic range. Okay, so the number of PCM bits transmitted per sample is determined by several factors, which are maximum allowable input amplitude, resolution, and dynamic range. Okay, and what is dynamic range? Is the ratio of the largest possible magnitude to the smallest possible magnitude that can be decoded by the digital to analog converter in the receiver. So the dynamic range can be expressed as Vmax over Vmin or Vmax divided by the resolution. Okay, resolution is delta V. And this dynamic range is usually expressed as dB value in decibel. So if you want to convert the dynamic range into decibel value, as like always, you need to multiply with 20 log. Okay. And next, the number of bits used for a PCM code depends on the dynamic range. Okay, so you need to follow this formula. Okay, where the minimum number of bits is 2 to the power of n minus 1. Okay, so this the relationship between dynamic range and the number of bits in the PCM code. Okay, so for example, this is number of bits, this is number of levels. You can calculate number of levels by using the formula L equals to 2 to the power of n. Okay. And for the dynamic range, you can calculate using the previous formula, which is 2n minus 1 equals to dynamic range. Okay, in dB. This formula, if you use this formula, the value of the dynamic range is not in dB, yeah? So you need to convert it into dB later. So let's look at the first example. For a PCM system with the following parameter, determine the minimum sample rate, minimum number of bits used in the PCM code, resolution, and also the quantization error. So you were given the maximum analog input frequency. So maximum analog input frequency means that input, this is input, so meaning that this is modulating signal, FM max. And this is maximum decode voltage at the receiver, positive plus minus 2.55. So this is the V min, and also you have the V max. And this is the dynamic range, okay, minimum dynamic range. So the first one, calculate for the minimum sample rate. So you know that Fs is equals to 2Fmx. This is the minimum, yeah. So 2Fmx is 4K. So you will get the sampling rate, the minimum should be 8 kilohertz. The second one is the minimum number of bits used in the PCM code. So you can use the formula dr in dB, because the value here is in dB, is equals to 20 log to the power of n minus 1. So this is 46. Okay, 46 divided by 20 here, you will get log 2n minus 1. And then 2.3 equals to log 2 to the power of n minus 1. And 2 to the power of n is equals to 10, 2.3 plus 1. And you will get 200.53. Okay, 200.53. And then you want to calculate for n. So n is equals to log 200.53 divided by log 2 equals to 7.65. So you approximate this as 8. So the answer is 8 bits. 8 bits is for magnitude. Magnitude. If you have a sign bit, then you need to add another bit. If you have a sign bit positive and negative, then you need to add another 1 bit. Okay, but the minimum number of bit here for the magnitude is 8. So next C, you want to calculate for the resolution. Okay, C, delta V, this is resolution, V max minus V min, L minus 1. So 2.55 plus negative minus negative 2.55 divided by 2 to the power of 8 minus 1. And you will get 0.024. Okay. And the last one is the quantization error QE. QE is delta V over 2. So delta V is 0.02 divided by 2. So the error is 0.010. Okay, so this is the answer for the example 1 for chapter 4. Next parameter is decoding efficiency. So it's the ratio of the minimum number of bits required to achieve a certain dynamic range to the actual number of PCM bits used. So decoding efficiency is minimum number of bits divided by actual number of bits multiplied with 100. Okay, so the number of bits must include the sign bit. And the last process is the encoding. Okay, so the encoding here is the process where the sample is divided into various levels coded into respective codes. Okay, so the samples, they are the same number of level are coded into the same code. So you can look at here, the number of bit is equals to log 2 quantization level. So you can also use this formula if you have the the quantization level and you want to determine the number. So this is example of binary number and 3-bit pulse code. So the first quantized level, the binary number is 00. So the pulse waveform is something like this, 000. Okay, so next the quantized level 2, the binary number is 001. Then the pulse waveform is 001, and so on. This is encoding. Okay, so next, this is example of binary number and 3-bit pulse code. So the first figure here, this is the input signal, analog signal. Okay, and this is the sampling pulse. And then this is the sample signal, PAM signal. So you can see that the PAM signal, it actually measure the value in the middle here. Okay, so that's why this one is, the amplitude is 2, this is 4, this is 5, 4 and 3. Okay, this is flat top slamping, and this is the quantized signal. So quantized signal, remember, it gives value, the level value. So this is 2, so meaning the value here is 0, 1, 0. 4 is 100, 5 is 101, 4, 100, and 3 is 0, 1, 1. Then lastly, then only it will convert to the PCM code. So how to write it? Basically, this is basically 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1. Okay, so since the the value in front is 0, so you can ignore the 0 here. That's why it starts with 1, 1, 1, 0. Okay, so this is the process of PCM. And for encoding, basically there are several techniques of encoding. Okay, so there are several techniques of encoding. Basically, if you look at here, this PCM here, this is basically non-return to zero and RZ level. Okay, but basically there are several other techniques for encoding. Okay, so this is the several techniques, encoding techniques. We have RZ, which is written to zero, RB written to base, AMI alternate mark inversion, split face Manchester, split face mark, non-written to zero level, non-written to zero mark, and non-written zero space. Yeah. So non-written zero mark and non-written zero space is we also call it as non-written zero inverted. So the difference is the difference between this line coding technique is basically, if you look at here, this is the PCM code. Okay, is the way you draw the PCM code. The PCM code is the same, but it's the way you draw the PCM code. So if you look at here, the return to zero is basically when you have one, logic one. So you have one, and then in the middle here, it will return to zero. And then one, return to zero. One, return to zero. This one is because it's already zero. So zero, and then this is one, and then return to zero. One, return to zero, and so on. For return to base, you can see that this is one. Okay, you have base. This is base, and you have zero at the bottom here. So one, return to base, one, return to base, one, return to base, and then zero, return to base, zero, return to base, one, return to base. Okay, so that is RB, return to base. And then we have alternate mark inversion. So alternate mark inversion is where you have one, and then you invert it. If you have one and one, then you need to invert it from positive to negative. So one, you invert it again. If the logic is zero, then you maintain. Okay, maintain. Then you have one, logic one. Then you invert it again. One, invert it again. Zero, maintain. So that is alternate mark inversion. And next is split face Manchester. So split face Manchester is, so this is one return to zero, one return to zero. But if you from one and then you meet a zero, then you need to change the face. Okay, split the face. So you can see here this face is changing. Okay, face is changing, and then you find, and then logic one, the face is changing again, and so on. So for split face mark, similar to split face Manchester, it's just that if you, the split face Manchester, the face is changing when one meet zero. But for split face mark, it changes the face when one meets one. Okay, when one meets zero, it maintains. So look at here, one, and you made another logic one, then it split the face. Okay, and then this split the face again. Zero, maintain. So this is split face mark. And this is non-return to zero. So the non-return zero, this is the basic one, non-return to zero level. So when the logic one is one, so 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0. So this is the one that we usually use, non-return to zero level. So this is non-return to zero mark. So the difference is basically is that this is one. When you meet another one, then you need to invert it. Okay. and then 1 again, you invert it again, 0 maintain. Okay, and so on. And then this is non-return to 0 space. Okay, so non-return to 0 space. So 1 1 maintain, and then 0. Okay, and then you make the 0, and then you back to 0, and so on. Okay, so this is the several line coding techniques for a digital transmission. Okay, so and the last slide is the transmission bit rate. So it's the rate of information transmission. So you can directly use the formula R equals to N Fs. So N is number of bits, Fs is the sampling frequency, and the transmission bandwidth for PCM is also equal to the transmission bit rate. So basically this is the end for chapter 4. So if you look at your slide, you have another part, which is chapter 4 part 3, but that one I won't prepare a video lecture for part 3 because it's not covered in your final exam, but you can still read through the chapter 4 part 3 as an extra information on the application side, okay, where this digital modulation is used in real application. So the application that is stated in chapter 4 part 3 is the application in the satellite communication. Okay, so you can read through that slide, however it's not covered in your final exam. Okay, just for your extra information to know where this digital modulation is used in real application. Okay, so later I will upload the tutorial for chapter 4. Okay, upload the tutorial for chapter 4, and then later we will discuss the chapter 4 in our next online class. Okay, so thank you.